Okay, so welcome everybody. So hopefully you can see my screen and hear me well. So today we've got a couple of sessions on Koopmans functionals. And so these are sort of divided a little bit between those two different workflows that I was talking to you earlier. So today in this first session, we're going to be looking at how we do these Koopmans calculations, specifically using these finite difference approaches for calculating the screening parameters. And so we'll look at calculations on ozone and on silicon. And later on today, after we've heard from Nicola Colonna's talk, and he introduces the density functional perturbation theory method, then we'll do some calculations using that approach as well. But for the moment, we'll be looking at this sort of larger workflow. And we'll be using the Koopmans software for doing this. Okay, so for tutorial 1, we're going to be looking at our ozone molecule, and we're going to be doing these calculations with the KCP code. So this is the supercell approach, and we'll be using Koopmans as well. So what we'd like to do is we want to extract the charged excitations of the ozone molecule. So we want to measure the ionization potential within the electron affinity, or more generally, just all of the different electronic levels. Of course, we're dealing with a molecule here, so it's not a band structure that we're extracting, they're just individual orbital levels. Yes, and so we'll be doing this with the Ki functional and with different screening parameters calculated with this finite difference approach. And so the main steps in this workflow are going to be we need to initialize the system using a DFT calculation, then we're going to calculate the screening parameters, and then we're going to finally perform the Ki calculation. And so what we're going to do is you can find the directory for these calculations here in the in the same repository as before, now in the day 3 folder, and will be in exercise 1. Great. And the one important thing that we need to remember to do firstly is we need to run the command conda activate Koopmans in order to have the Koopmans code at our fingertips. So this is specifically to do with the way that we've installed Koopmans on the Quantum Mobile. Okay, and then the way that we run this calculation is we're just going to be running the calling Koopmans and running it on this input file, ozone.json. So probably before I actually run this, let's have a look at this JSON file. So I might just pull up the screen to be a bit larger for this bit. Okay, so Koopmans takes a JSON file input. So I apologize for introducing another sort of file input. And I know we've seen a lot of these throughout the 3 days, but this is a slightly different format to the sort of style that we've seen earlier with the Quantum Espresso input files and the Linear 90 files, but it's sort of, it contains exactly the same information, and basically you'll be able to see it's very similar. And if you're familiar with Python, this is just nothing less than a nested dictionary. So it's the JSON format, so which is a much more universal format than any of the other input files that we've seen so far. And so the input file for Koopmans breaks down into several blocks. The first block is the workflow block, and this contains keywords that sort of define the nature of the workflow that we're going to run. So things like, okay, let's use the Ki functional. The methods keyword tells us how we're going to calculate these screening parameters. So that's going to be this delta SEF method. We're going to tell it how to initialize our variational orbitals in our system. We're going to tell it whether or not to run from scratch or not. And we can tell it how many self-consistent loops to do for calculating our screening parameters. And as well, we can direct it to use a specific library of pseudo-potentials. And then beyond the workflow block, then there are just a couple of other blocks which sort of contain the same sort of standard information that you need to specify the system that you're looking at. So here, there's an atoms block where you specify things like the cell parameters and the atomic positions. And finally, here at the bottom, we've just got a few calculated parameters that we specify exactly, things like the energy cutoff. So this is the sort of parameters that actually define what's going on under the hood when you run quantum espresso. So it is a slightly different syntax to the stuff that we've seen earlier, but we can see, all of the full information about this input file is on our website, koopmans-functionals.org. Great. And I see there's a question from Antimo that I'll just anticipate. So the Koopmans code can only be used with norm-conserving pseudopotentials. And then there's some way of getting the code to interface with these so that you can just access them with the sort of pseudo library keyword, but it's norm-conserving pseudopotentials. Okay. So what we're going to do is we're going to now run this calculation. So let me now pull up this terminal. And like I said, so here's that input file that we were looking at earlier. So it's
Sorry, Edward. Sorry,
yes?
Edward. In the second part of Antim's question, it's about nonlinear core corrections.
Yes, nonlinear core corrections are supported.
Okay, thank you.
Sorry, I missed that. That's just a glance. Okay. So here's the same input file as we had before. And so simply running this calculation is just a matter of calling Koopmans and then ozone.json. So, and then you run it like that. So, and what's going to happen is in the background, Koopmans is going to call different calculations as we go along. So here, it's just printed out the header. And now once we've got past the starting information, we've got some information. So here, now currently it is running a DFT initialization step. And so it's going to run that calculation. And then once it's done that calculation, it's going to proceed to the next one. And so exactly. And so it's what's actually happening is if I just open another terminal and I go to this directory, is now we've got these different directories. So it's created this init directory within which we can now see the different input and output files. So for example, the first calculation was this init/dft init nspin1. So if I look at this file here, I can see the actual quantum espresso file that ultimately what's happening is that this, well, probably before I look at the output file, I'll look at the input file. So this is .cpi. So often with these files, we've got files ending with an I correspond to input files, files ending with an O correspond to output files. So here's actually the quantum espresso input file for the KCP code. So this is a lot more familiar with this is the same sort of quantum espresso format that we've seen earlier this week. But you can see there's a lot more information here than was present in the original JSON input file. And so this is because Koopmans has populated this input file with all of the different information that it needs. And so now we've got an output file. And so here it's just got a header with different bits of information. And then once you get beyond the sort of the parameterization of the problem, then here we get to this step here, where maybe I'll make this window larger so it's not overlapping. So here we've got the stage where we're now performing our conjugate gradient minimization of our electronic states. So you'll remember from my talk, where we've got to minimize the total energy with respect to our different orbitals. And so that's precisely what's going on here. We're iterating through, and you can see that we're monitoring the total energy of our system as we go from one step to another. And you can see this delta E as we go through, as it drops and drops and drops. And eventually here, it's dropped below the threshold, and so it's converged. So we've done that for the occupied orbitals, and then here we've got again the conjugate gradient minimization, but now for the empty states. And so again, we see a similar minimization procedure eventually until we get to the end of the calculation. And then, as per usual with these sorts of calculations, as we see some summary of the different energy components, the different eigenvalues, and some timing summaries before the end of the file. Okay. Right, so that is sort of a typical input file. So now, let's have a look at what's happened in the background as I've been running this calculation. So we've got firstly, we've got this initialization procedure. So here we've got these three calculations. This is the DFT init in spin 1, DFT init in spin 2 dummy, and DFT init in spin 2. This is nothing more than just initializing our system and doing a DFT calculation. We've just split it into 3 steps, because in this particular instance, we're doing a calculation on a system that is non-spin polarized, but we need to do a spin polarized calculation for the purposes of adding and removing electrons, ultimately. But we want the system, at least the neutral system, to be spin symmetric. So one of the ways that we can just make sure that these calculations are especially stable is we do an n spin equals 1 calculation first, and then from that starting point, so we've got a spin symmetric solution, then you can restart based off an n spin equals 2 calculation. So that's just a technical step, but basically all that we're doing with these 3 calculations is we're calculating the ground state density at the PBE level. So here's the details on the file that we saw. And specifically, it was looking at, if we look, say, for example, and now the n spin equals 2 calculation, we can see again this conjugate gradient minimization of our electronic states, and you can see within it as the energy drops down, and we have ultimately get our energy within the threshold. And then at the bottom of our file, we have a description of what the HOMO is and the LUMO is, and all of these eigenvalues. Now, of course, these are the DFT eigenvalues. These aren't yet the Koopmans eigenvalues, because this is just a calculation using PBE. Okay. So now, once we've done this initialization, we're going to do the step where we're going to calculate the screening parameters. So this is this additional step where what we've got to do is we're going to have to solve this equation here. So what we need to do is we have some guess, some trial alpha, and then we need to compute all of these different quantities. Now, if you remember this, so these sort of expectation values, this is what I called those lambda values earlier. And so all of these quantities can be obtained from a trial Koopmans calculation for the neutral system. So this is this calc alpha Ki. So here finally we're doing a Koopmans calculation, but just with a trial alpha value. And the one remaining ingredient that we need to calculate is the total energy of the system when we remove the electron from that particular orbital. So that's what all of these calculations are here. So here we're going one by one through our orbitals, orbital 1, orbital 2, orbital 3, orbital 4, and we're removing an electron from that particular orbital, and then we're trying to calculate the total energy. So you can sort of see this implicit in the file name. So it's calc alpha / orbital 1 / DFT n-1. And so if you're interested, you could open specifically that directory and that file name, and you'll see the corresponding quantum espresso input and output files that correspond to that calculation. But ultimately, all that we're interested in from that calculation is the total energy. And so the code is just calling that command, running quantum espresso, and then it's going to extract from that calculation the total energy. And so once we get down to the end, here we've got a tabulated table here where it's got the alpha values that we've calculated. So you can see at the 0th step, so these are every alpha value is 0.6. So this was just our trial, our guess value for alpha. And now it's worked out, having done all these calculations, that the alpha value for orbital 1 should be 0.656, and the one for alpha, the second one should be 0.72, 0.73, and so on. So it's gone through every orbital, it's calculated the appropriate value of alpha. It also shows the sort of delta epsilon I, the change in total energy minus this epsilon I. So what this is just a difference between this quantity here and this quantity down here. And so this is sort of a measure of how far away you are from convergence. Because if you imagine that those two terms are exactly the same, then this entire fraction evaluates to 1, and it means that your trial alpha is, sorry, the final correct value of alpha is equal to the trial value of alpha that you put in. So we can see for when I tried 0.6, 0.6, 0.6, this was the degree of error in this sort of error measure. So then finally, having obtained these alpha values, then we do our final Ki calculation. Probably before I say that, in principle, what you could do here is you could increase the keyword n max SC steps in the input file, and you could get it to you could get the calculation to iterate further and recalculate the alpha parameters based off these ones here. In the case of the Ki functional, this isn't necessary because the Ki functional leaves the total energy unchanged, and all of these quantities don't change as a function of alpha. So actually alpha converges instantly with this calculation. And so in fact, if you were to increase this quantity, you would actually see that at the next step, you'd get exactly the same values of alpha, and this error message would, sorry, this quantification of the error would go precisely to 0. Okay. And now finally, we get to the final Ki calculation. So we've calculated all of our screening parameters. And so now we have our final solution. So if I go and I look in final/Ki final, and I look in the output file, which has got the final value, it's .cpo. So here we go. Here's that calculation. So it's the same as, much the same as before. We've got this header with all of this different information about the way the calculation's set up. And ultimately, here we go. We have our conjugate gradient minimization of our electronic states and of the empty states. And note that because the Ki functional doesn't change the total density, that actually this converges instantly. But now we've used our but now we're using our alpha parameters that we've calculated. So here we can now see finally our eigenvalues as given by a Koopmans functional. And so these are just sort of obviously written out in this file specifically. And let's now just compare those to the density functional theory. So if in this directory, there's these scripts that have just been prepared. So I can just run get be.sh, that's just going to extract them from the input file. And now I'll just run new plot of this be script. So you can do this yourself. And what you'll see is this plot here. So here we've got the DFT values of our individual orbital eigenvalues. And we've got in red the results that we got for our Ki values. And we're comparing these against experiments. And here you can see that the Koopmans calculation has done very, very well at getting these compared to experiment, compared to the KI, this is compared to, sorry, the base DFT functional. I think this script is also set up to generate another plot here. It's sort of showing the similar sort of thing here. We're just showing the relative error. So we've gone from having a relative error of, up to 40% in these eigenvalues down to an error of a couple of percent at most, and even for some of the best ones, fractions of a percent. I think that takes us to the end of tutorial 1. So I might stop here and see if we've got any things that we'd like to talk about before moving on. So were there any questions that I should address, Yuri?
Actually, so far there are no particular questions. So
okay,
if you want to move forward, there is Omarus typing. Actually, several people are typing. Let's wait
okay.
1 or 2 minutes.
So I think it'll be worthwhile pausing
Yeah.
at this stage, just because, so this is sort of a typical Koopmans calculation for a molecule. So our next one is going to be on silicon, so it's going to be slightly different because we'll be dealing with a periodic system. But yeah, so let's pause here, and I'll let people have a look at the different input files, try and look at these plots for themselves, and I'll answer a few questions, and then we'll so is the in scheme. So by end, do you mean the machine learning scheme? And yes, okay, no. So we're in the process of implementing that and distributing it. So it's in a private fork, and eventually it's going to be, well, within a couple of weeks, it will be there and available for you to use. Do you have any accompanying package to calculate transport coefficients using data? No. So this is sort of what this produces is the band structure results. If you want to feed that into some other code to extract transport coefficients, you could do that, but that isn't something that we've explored. So yeah.
Maybe I can add a small
Yeah,
on
sure.
this transport coefficient. So something that we mostly for solids actually. So we work in a Vanier base somehow. So actually, what can be easily done is to export the Koopman Hamiltonian in a Vanier base and then import it in codes like bootstrap, so that works in a Vanier basis where everything is already implemented. So it's not something that you can do inside Koopman, but it shouldn't be not that difficult to interface the output of Koopman with existing code, as Edward was saying. And bootstrap is probably one of those code that computes transport property in an easy way. Okay, just
Yeah. I've got some practical issues that I think is best dealt with in Slack. Okay. I think I'll move on to our second example. And let the other tutors take care of the questions in Slack. And so this is our second example, is going to be looking at the calculation on silicon. So let's have a look. So now let's go into exercise 2 directory. So here we're going to now look at silicon. And so there are a few differences to what one has to do when you're dealing with a solid compared to when we're dealing with a molecule. So again, as before, we've got to do the DFT initialization, but now there's the additional step where we perform a vaniorization. And then once we've vaniorized the system, we do perform the screening parameters and the final KI calculation. So what was happening before in the molecules, which meant that we didn't have to do a vaniorization, is there we were just using the Cohen-Sham states as to initialize variational orbitals. In a solid, we'd like to use Vanier functions instead. So that is why we've got this additional step. And finally, once we get to the very end, what we'd like to do is we want to extract the band structure. However, what we're doing in this sort of finite cell approach is what we do is we go to a supercell and calculate the total energy differences when we remove one electron. And so if we just sort of stopped at that point, we'd have a whole lot of different eigenvalues that are sampled at gamma only. So that sort of is enough to tell you what the band gap is, but it doesn't tell you what the entire band structure looks like. And so what you can do is we can go back and take these supercell eigenvalues just sampled at gamma and work out what the band structure looks like for the primitive cell, but now with the eigenvalues across different K values. So again, let's just have a look at the input file, and I'll just make this screen larger again. So here it's much the same, but we've just got a few differences in the workflow block for a start. So here we've got this MP correction flag, which is in this instance, we've got it set to false. And so this can activate or deactivate the Markov-Payne charge corrections for these n+1 and n-1 calculations. Like I said, we want to make sure that we avoid spurious interactions between these adjacent images. In the case of silicon, actually, it's got such significant screening that the Markov-Payne correction is not necessary. Here we've got initializing our orbitals to be these maximally localized Vanier functions. And actually here we've provided specifically a value for our guess for the screening parameter. So here we're going to use 0.077. And then the final thing we're going to do, and I think this is not actually something that we've talked about yet, is we're going to group our variational orbitals. And so what I mean by this is that in our silicon, in our bulk silicon, we've got a whole lot of different orbitals that are actually translationally and rotationally equivalent. So we don't need to go through every single orbital in our system and calculate a value of alpha for that orbital, because there are a lot of them for which basically you're performing exactly the same thing and you're going to get the same value of alpha. And so what we can do is we can group our orbitals together. If we know that these guys are equivalent, then we can just say, okay, if I know orbitals 1, 2, 3, and 4 are exactly the same, except modulo some translation and rotation, which isn't going to affect my alpha value, then I'll just calculate alpha for one of them. And so this can dramatically, and like we said, that the process of calculating the screening parameters is the most expensive part in these calculations. And so if we can do these sorts of things where we only calculate alpha for some orbitals and use the alpha values for equivalent orbitals, then this is going to really speed up our calculations. And so in this instance, what we've done is actually, we've told it that we're going to, we specify our orbital groups with a list that's as long as the number of orbitals in our system, and basically orbitals that have the same, corresponding with the same integer, are grouped together. Now this is sort of, so in the case of silicon, we already know, based on, if you've gone away and done a vanarization, we know that we've got 4 sp3 orbitals that are all equivalent, that are occupied, and then likewise for the empty states. So alternatively, if you sort of don't know what your system looks like, there's another way where we've got an algorithm that can actually work out this orbital grouping for you, and it's done using this keyword orbital groups self-Hartree tolerance. And so what it does is it groups orbitals based on what their self-Hartree value is, which is a sort of a proxy of how spread out the orbital is. And so if 2 orbitals have got matching self-Hartree values, then chances are they're going to be actually just rotationally and translationally equivalent. And so you can do that if you like for your own systems. And again, I'd direct you to our website for a full guide about how this is done. I should have actually had this going on in the background while I was talking, but let's just do that now. So I'm just going to do Koopmans, but now I'm just going to run it on the silicon calculation. Okay, Oh yes, and so the other thing that's going to be different to the input file for the molecule is that now we also need to, we're performing a venerization, so we need to specify the way that we're going to, the projections that we're going to use. So here in this Vanier 90 block, sub-block of the calculated parameters, there's a block here where we specify the projectors here. There are a few other blocks that you'll see down there. There's a smooth interpolation method that I'll discuss later on, and some stuff to do with tweaking the plots that it generates. Okay, so now we're going to, now hopefully we've all managed to start this calculation to run. And so here, if I look at this file, we've got, now it's slightly different. So instead of just starting off before in the init directory, now we're starting off in the Vanier directory. And so there's a couple of calculations that we're doing. We do an SCF calculation to start off with. So again, this is just PBE, and a non-self NSCF calculation. And then this is exactly the same as what you saw on day one. So this is now the vanierization steps. So first we do a pre-processing step with Vanier 90, then the PW to Vanier step, and then the vanierization step. And so if you go into those directories, you'll see that there are Vanier 90 files that have been generated automatically with the requisite input files and the corresponding output files. The thing that's super important for Koopmans functionals is that we do this vanierization separately for the occupied and the empty subspaces. So before in the tutorial, for the Vanier 90, sometimes we were running calculations which included both empty and orbitals, or empty and occupied orbitals simultaneously. Now, this is we need to do these separately for Koopmans calculations, and you can do this using the exclude bands keyword in Vanier 90. And so if you look inside those input files, actually, maybe I might do that now. So if I go into exercise 2 and I go into the init Vanier, and then say I'll go have a look at the occupied files. And here I've got all my different input and output files for my calculations, but van.wn is the input file for my Vanier 90 calculation. And if I open this, you can see that this is exactly a Vanier 90 input file. And we can see here that I've excluded bands 5 through 20 for this particular calculation. So that corresponds to all of the empty bands. And if I look not in the occupied, but now at the empty, now instead we're excluding bands 1 through 4 for this particular calculation. But you don't really need to worry about all of this sort of setup. As long as you've written the input JSON file, it will generate these keywords automatically. Okay. So now if I look at, so I've talked about the vanierization, so the standard PBE calculation plus the vanierization. Then what we need to do is we now need to take these Vanier functions, which are defined in on a primitive cell, because we've done all of these calculations on a primitive cell, but now we want to extract these and populate a supercell with these Vanier functions. And so there's a code that's doing this automatically under the hood. So this is called van to KCP. So you don't really need to worry about the details, but precisely what's going on here is we're just taking these Vanier functions that are defined on the grid in the primitive cell and expanding them out to the supercell. And then we're back into the standard steps that we saw for ozone. So we're going to run our trial Koopmans calculation, and then for each orbital in our system, we're going to do this calculation where we remove or add an electron to it and measure the change in the energy that happens. So the one difference that we'll see is that we've actually got these, for instance, orbitals 1 through to 31 are now being skipped because we said we had grouped them all of those orbitals together using that orbital groups keyword. And so now it's going to skip orbitals 1 through 31, and it's only going to calculate alpha for orbital 32. And likewise, it's only going to calculate so that's all of the filled orbitals. The fact that there's 32 orbitals now rather than the 4 orbitals of earlier is just because we've gone up to the supercell. And the dimensions of the supercell is just defined by the K grid that we used in the primitive cell. So these 32 are our filled orbitals, and then 33 through to 64 are our empty orbitals. And so likewise, we do a calculation on orbital 33, and then we just skip those from 34. And so we'll see if I now look at the printout of the alpha calculations, then I've now got the same value of alpha that's been given for all of the first orbitals, and for the last orbitals, it's worked out some other value. So here you can see the real importance of calculating alpha from scratch. So if you remember for water, the values that we were getting, they were about 0.6, 0.7. Here we've got values that are about 0.1 or even smaller, 0.04. And so these parameters, much like the plus U in DFT plus U, these parameters are very system dependent and obviously can be orbital dependent if they're an equivalent. So it's super important that we calculate these things ab initio. And we saw with Yannick what can happen if you just use some sort of average value in place of calculating these from scratch. But again, this is much the same as once we've done that calculation, we've got our final KI calculation. We've just got some warnings that are throughout here. That's to do with it automatically generating some particular keywords. If you wanted to disable those warnings, you could just provide these keywords explicitly in the input file, but it's nothing to worry about. It's just something to be aware of. Okay, so I think I might have. Okay, great. So now we come to the. I actually know this is a bit ahead of what I wanted to talk about. So now we should look back at this. And so this final step is the post-processing step. Actually, do we have some slides on this? Yes. We've got, so for a, like I said earlier, we've now done a calculation in a supercell. And the but this is now only with gamma sampling only. So we now want to go back to a primitive cell, but now with the full, to extract the full band structure. And so that's what these post-processing steps do. So what we're doing now is we're doing a new vanarization of our system, but also we're going to do this at a higher resolution K grid than before. And so this is because we're using this so-called smooth interpolation method. And so what this does is the following. So what we're going to do is we're going to construct a Hamiltonian as before. And the way that you sort of construct this Hamiltonian at some sort of arbitrary K point is by performing these sorts of integrals here on your Hamiltonian, where these these bras and kits are our Vanier functions. But what you can do to sort of get around a few issues with, so probably what I should say first is that obviously we want to converge with the number of K points in your grids. So this is super important to make sure that we're converged. But the larger and larger our K grid is, the larger and larger our supercell needs to be in our calculation in order to match the corresponding K grid. And so this quickly becomes quite expensive. However, we saw in the lectures that actually what the Koopmans potential shift does is, at least say in the instance of Ki and for the filled orbitals, is just a rigid shift in the potential of individual orbitals. So actually, in terms of K space, these potentials are not rapidly oscillating in K space. So what we can do is we can construct a Hamiltonian where we separate out this construction into two parts. We can construct the underlying DFT contribution to our Hamiltonian with, and we can calculate this on a superfine K grid. and then we can compute just the Koopmans contribution on our original supercell grid. And so what's going on here in this post-processing step is we're doing an additional vectorization, but now on a superfine grid to get our DFT Hamiltonian on a superfine grid. And then to this, we're just going to add the Koopmans correction as we've computed it on the original cell. And so this is a nice little trick that we can play in order to get better band structures, but only at the expense of doing a higher resolution K point at the DFT level, rather than having to do it at the Koopmans level, which would be more expensive. And so you can see here, we've compared the result that you get without this sort of smooth interpolation compared to the value to what you get with the smooth interpolation. And the blue is the result that you'd like to get, the result you'd like to match those exactly. And so clearly with the smooth interpolation, we do a better job. And so we can see if we look at these band structures that basically the net effect of the Ki functional is to widen this band gap. We go from the red curve down to the green curve. As a little added bonus, if you like, we could you can go away and carry out the perturbative KIPZ calculation. So, like I mentioned in my talk, this is evaluating the Ki Hamiltonian on top of the Ki solution. Sorry. And so what was I saying? So we don't do any further optimization. And so what we can do, yeah, let me just move this to the side of the screen. Is you can, let's just change in my JSON file. I could change the functional to PKIPZ, and I'll change from scratch to be equal to false. And then I could run this calculation. The one thing I should probably do before doing this is actually have a look first at our Ki results. So there's this script here called plot_bs.py. And so what I can do is just run that script, and I'll look at it later. But first, let's have a look at the band structure. So this has just generated a PNG file called bands, and that's generated, well, that's exactly what we saw from earlier. This is our nice new band structure. This plotting function, it's worthwhile sort of spending a little bit of time looking at this plot band structure script. So this is just a Python script. So for those of you who are familiar with Python, it should be quite easy to understand what's going on. And what we're doing here is we're loading in our workflow object from file. So when we run any workflow, it will generate this file called a KWF file, a Koopmans workflow file. And so this object is just something that contains all of the information about the workflow that was run. And you can sort of load it into Python, having run a calculation earlier. So what you might want to do is you might want to run your Koopmans calculation on some cluster somewhere. And then once you've done the cluster, you could copy over the KWF file to your local machine and open it up in Python and have a look around at what it looks like. So for example, if I open a session in Python, then and if I just from Koopmans.io, I'm going to import the read function. And now I'm going to read in my workflow. So now I've got this object here in Python called my workflow object. And here I can see this is a single point workflow with silicon. And I've run it with these particular parameters and these different K points. And so you can just play around with this, and this is sort of makes it very straightforward to, perform post-processing on your calculation and extract anything that you're interested in. So it's got all sorts of things like we can have a look at, well, for example, what functional it was run with. So it's got the ki functional, and I can look at the different calculations that were involved in the workflow. And so here's a list of all of the different calculations that were run. There's my initial SCF calculation, my NSCF calculation, my post-processing calculation. And so we've got a whole lot of different calculations there. And so this is sort of all at your fingertips if you want to load in this KWF file. So let me just exit from here. And so this is precisely what this plot BS script is doing. So this is sort of a different approach to what we saw earlier with the first exercise, where we just used a crude bash script to extract the results directly from our Koopmans result. Sorry, 1 second. Okay, so before we were using just bash scripts to extract the results directly from the Quantum Espresso output files, but under the hood, the Koopmans package is already having to do that process of passing information from the output files of Espresso calculations. And so instead, we can just have all of this in a convenient format for Python. So if I look at this plot band structure script, it's doing exactly that. So it's just importing the Koopmans read function, calling read, and then extracting from the list of calculations, this -1 means the last calculation in the full workflow. I'm going to extract the results from this calculation, and specifically I'm going to extract the band structure. And so this is going to return to me a band structure object. And I can then do things like plot this. And so, I mean, the precise details are unimportant. You can sort of look through that in your own time, and happy to answer questions. Basically, what's happening is all of this is ultimately using the machinery of the atomic simulation environment. So you might notice that if you load this up, you'll see that the band structure object is a ASE band structure object, as they define in that package. So that does the band structures. So I think with that, how are we doing for time? I think we've got 10 minutes, so maybe I might stop for questions.
Well, actually, there was a question from Terso, I'm not sure, but is about how to generate the JSON input file. So maybe you can show the QE to JSON utility.
Yeah, sure. I mean, hopefully, yeah. Okay, so yeah, I haven't actually tested this. So let's just say I've run a calculation on silicon. I've just a quantum espresso calculation. So an example input file is going to be exercise 2 init 1 linear. So here I've got an scf.pwi file. Yeah, so you might have a file like this for your JSON file. We do have a utility called QEI to, and it's just going to tab complete. I wonder if it's not on the path. Okay, so maybe. So Koopmans comes with a utility, or QE, oh, it's not QEI, QE to JSON. Maybe if I don't need to do the QE to, exactly, QE to JSON, and then I just provide an input file for that, and I'll just run that there. Oh, and I forgot an output. So and then I provide an out.json. Great. So having run the script, now it's generated a file called out.json. And if I look at this, here is the JSON file that is automatically generated. So it's populated some sort of naive guesses for what the appropriate value for the task and functional. It's added all sorts of different keywords. And so it's, yeah, so basically you can use this utility to take a quantum espresso input file that you've chosen and to generate a JSON file for it. Now, the important thing to do is to always check what's in this particular file. So it will have populated it with different things, and it's imperative to make sure that it's set up it exactly the way that you'd like to. And you'll often, I mean, for example, to do anything apart from the default behavior, you'll want to change things in the workflow, for instance. Yes, so that's the QE to JSON utility that sort of comes with Koopmans. Great. Were there any other questions that it would be good to discuss?
Not yet, but at some point I saw like again, yeah. Abdeslam. So in hands-on of this day 3. Yeah, I see the two yeah, maybe you can answer that question.
Yeah, sure. So just to be clear, so KCW is one particular implementation of Koopmans functionals. So it's just calculating the screening parameter in a slightly different way. So all of the calculations that we do later on this afternoon, we're going to use pw.kcw.x, but you can also use the Koopmans package to run these calculations. So the Koopmans package is just basically a Python script, right? It's ultimately underneath the hood. It's calling the KCP code, it's calling the Vanya 90 code, it's calling the PW code. So just to draw that distinction, so this sort of Koopmans sort of wraps around that and just manages all of the workflow. So later on today, we'll be using KCW. And so here in this tutorial, we've been using the KCP code. So this is the one that does the calculations in the supercell. And so they use slightly different formalism in terms of the way that we calculate these screening parameters. And no doubt Nicola will get into this in his talk after lunch. Yes, so hopefully that answers your question. I see another question about the QE to JSON checking the compatibility of the pseudo potentials automate. No, so it's sort of it is on you to check the pseudo potentials. There are Koopmans does do some cursory checks on the pseudo potentials, but it is no guarantee that your calculations are going to be perfect if you use Koopmans. You still need to sort of be careful and use the appropriate pseudo potentials. And to use the right K-grids and to make sure that your Vanya 90 calculations are converged. It will complain if a calculation isn't converged, but it's up to you to make sure. So it will complain if, say, a Vanya 90 calculation fails, but it's not going to sort of do a convergence test for you, for instance. To run okay, so maybe let's do the KIPZ, the PKIPZ calculation. In principle, no. That you don't need to run a KI calculation first, although practically, basically, it's so yes, you do need to run a KI calculation to do a PKIPZ calculation. In terms of what the PKIPZ calculation is evaluating the KIPZ Hamiltonian on top of the KI results, right? So you need the KI results to do PKIPZ. But I don't need to have sat down and typed it, run the KI calculation beforehand. So in principle, let me just go back to the base directory. I could just take this could have been my input file. I could just provide PKIPZ, and I could have from scratch equals to true, and it would run a PKIPZ calculate. It would just sort of generate that for you. But in the process of running that calculation, it would first do a KI calculation because that's what you need in order to do your PKIPZ calculation. So just because we've happened to already do a KI calculation, we could now quite easily do a PKIPZ calculation. So let me just do that. si.json. I believe I updated. Let me just double check the input file. Yes, so that's now updated and it's from false. Hopefully you got that from earlier. The instructions here are on the left-hand side of the screen, but now you can see already it was very quick. So it generated all of this stuff, and it's actually deciding not to run the vanarization because these files were already in my directory from the KI calculation. So it's going to skip over the vanarization because it was already done. It's going to skip over all the calculation of the screening parameters. It's going to then finally do a KI final calculation because you already have that. But now it's going to do, finally, it arrives at this point where now I'm going to do the PKIPZ calculation. And so this is where it needs to sort of start doing new calculations. When you construct the orbital densities, look at orbitals per K point, or you construct an orbital density that is integrated over the Friedmann zone. So when we construct, so in the KIPZ calculations, when we construct these orbital densities, so for the large part of the calculation, we are existing entirely within this supercell, where we have orbitals that are just defined at gamma. And when we transform back into we're just always thinking about variational orbitals, right? Which are these Vanier orbitals, which are sort of localized orbitals that are just defined at gamma. Now, when you sort of go back and into this post-processing, we then have things that are resolved in terms of K points. Well, sorry, we don't have orbitals that are resolved in terms of K points. We always are dealing with this localized basis. Yeah. Okay, so hopefully slowly this is working its way to the finish of the KI calculation. So is it correct that we're due to finish at 12:15?
Yes. Yeah.
Okay.
Yeah. This was the original plan. So then we have a lunch break. No, 12:45 actually. Wait. Yeah, 12:45. So in principle you have
I mean, we have another half hour.
I think it's 12:30 actually.
Yeah, it's 12:30.
Oh, about it.
So
Yeah.
15 minutes left if you need.
Okay, thanks.
Okay, so there we go. So now the PKIPZ calculation is finished. And once again, if I want to, we can run the script for generating the plots. And have a look at the band structure. And I probably should have kept the original one to compare, but it's not going to be wildly different, at least if you look at this. Maybe if we extracted the band gap exactly, well, maybe we could have a look at that. Is that information going to be readily? Okay, so if I look in the final directory, then I've got my KI final.cpo file, where if I look inside of this, I can see I've got an electronic gap of 1.2876 electron volts. Whereas if I look at my PKIPZ calculation and look at the bottom of the file, it's changed slightly, so from 1.28 to 1.32. And I'm sure if you sort of plotted those two band structures on top of one another, maybe you'd start to see slight differences. Okay, well, I think we've presented everything that we were hoping to present. I think we can just continue to answer questions. And then, so I'll continue to answer questions here. We're not going to present anything more in terms of the tutorial itself. And then, so maybe we can give people without any questions an extended lunch break. And we'll continue here through to 12:30 with any questions that come up.
Just wanted to say that I just tested, I mean, this was not part of the tutorial, but I just tested on the virtual machine the KIPZ calculation, which normally is a bit more expensive. So we were not planning to do it today, but it seems to go. So if you want to have fun, guys, and try also KIPZ, you can go on. There's maybe a question coming from Nitish.
In the band structures in the so
sorry, could you just speak it up loud for recording?
Sorry?
If you just could repeat the question loud.
Of course. So the question is, in the band structure showing the corrected Fermi level calculated using DFT was near to the valence band maximum of Koopmans, it was near the conduction band minimum. So if I'm just going to open this band, I think this is just a technicality. So we've just the dashed line that we've shown here that we've aligned everything with is the valence band maximum. So that dashed line is indicating nothing less than the valence band maximum. So for the DFT solution, so it's just the way that the data has been presented. So that's not a corrected Fermi level. That is just the DFT Fermi level that we're plotting there, and everything else is, well, the DFT valence band maximum.
Okay, thank you. All right, do you think we can stop here, or shall we wait a little bit more?
Yeah, we can stop here, and I can make sure I answer any questions in the chat. That's probably the best way of doing it, rather than waiting for things to drip in.
Okay, very good. As indeed was pointed out by other organizers, the day is long still.
Exactly.
So 2 invited lectures in the afternoon and 1 lecture by Nicola and continuation of hands-on. So probably it's
long
good
but exciting.
Yeah, it's good to have extended lunch break. So
Sounds like a very good idea.
Yeah. But thank you so much, Edward, for this very nice and clear hands-on. Thank you, Riccardo. Thank all tutors answering on Slack. And thanks again for all lecturers of this morning. And see you all after lunch in the lecture Zoom webinar. And thanks again.